So for the bulk of this session is my speaking Singla. It's about second confidence and stochastic problem.
Hello, everyone. Yeah. Firstly, thank you for staying till the last hour of the session. Try to keep it like a bit level. So yeah, this is a lot about like different problems under uncertainty. This joint work with Aviad Rubinstein from Stanford. So firstly, in this work, we'll focus on packing problems under uncertainty. So what do I mean by a packing problem? Think of it like you have n elements. Each element has a weight, and you have some downward closed feasibility set system. Your goal is to select a max weight feasible set. So every element has a weight, like things like classical examples like max weight matching and so on. So you have a downward closed set system. Each edge has a weight, each element has a weight, and you want to select a feasible set of maximum weight. The challenge, however, here will be like we'll be working with arbitrary downward closed set system. I don't want to make any assumptions like it's a matching, it's a matroid, intersection of matroids. It could be arbitrarily complicated downward closed set system. And we are interested in finding a max weight solution. So this problem, of course, we are interested in the weighted setting, but often such problems are also studied in the unweighted setting, or the binary setting, where every element has weight just 0 or 1. So alternatively, you are trying to now find a max cardinality or max size solution. So like in matching, for instance, max size matching versus max weight matching. Often the unweighted problems are easier, but they capture some kind of like core difficulty of the problem. And then you hope to extend the things to the weighted setting. So we'll be focusing on such packing problems in the weighted setting uh, under uncertainty. And even in under uncertainty, there's like a standard reduction even for general arbitrary downward closed system, how to reduce a problem from weighted to unweighted setting, up to losing a log n factor. So the claim I'm making is that if you have a problem where you can get, let's say, alpha approximation in the unweighted setting, I can get a alpha log n factor in the weighted setting. And the trick, it's like from a standard textbook trick. Literally imagine like all the weights are between 0 to 1. I'm just going to consider powers of 2, like 1 to 2, 1 to half, half to 1 quarter, 1 quarter to 1/8, and so on. So there are only like roughly log n buckets I need to consider, because any weight which is smaller than 1 over poly n, I can just ignore it. It contributes very little to my value. And now out of these log n buckets, I can just randomly pick one of these buckets and just solve my unweighted problem on just that bucket, because all the weights in that bucket are like within a factor 2. So that gives me like a log n approximation to my problem. Like by losing an extra log n factor, I've reduced my weighted problem to the unweighted. And the goal of this work was to basically study like when is this extra log n factor? Can it be avoided, or like do we have to really lose it? So broadly, we are interested in general packing problems under uncertainty and trying to solve them for weighted problems. Let me now make it more concrete. So the three problems we are interested in this work, which we progress on, are the secretary problem, the profit inequality problem, and the stochastic probing. So the precise details of these problems don't matter, but these are all like very well studied problems under uncertainty, having tens of papers or even hundreds of some of them. So maybe like to keep one in mind, like let's consider the secretary problem. So here the setup is it's an online version of the problem. So you have again these n elements. Upfront, however, the weights are not known. So these elements come one by one in a uniformly random permutation, like one of the n factorial permutations. As soon as an element comes, you need to, its weight is revealed, you need to immediately accept or reject it, and while always being feasible, trying to maximize the total value. The question is, compared to the hindsight optimum, what can I get? And again, we are interested both in the weighted and the unweighted problem. Unweighted means like the elements have weights 1. So for each of these three problems, previously basically for the unweighted problem, we knew that the right answer is roughly a log n. Up to a log n factor, we knew that the right answer is log n for each of these three problems for the unweighted setting. Using the standard trick from last slide, you can get a log square n guarantee for each of these three. Immediately follows. But the main question that was not clear is like, do I really have to lose this extra log n factor? Is the real answer like maybe closer to a single log n, or is it like the real answer closer to log squared n for each of these three problems? And that's actually somewhat funny. Like even like let me even tell you the answer. Turns out, so for one of these three problems, the answer is a single log n, and for two of these three problems, the answer is log squared n. And for people like if you ask them like who work in these area, like it's upfront like not clear which of the three problems should be easier. So that's what where we started off with. And so the interesting thing is, turns out like the same intuition basically, like the intuition which we are calling the big decisions first principle, kind of dictates the answer for all of these three problems. And the principle or the intuition is somewhat quite natural. All it says is that somehow, like under uncertainty, you want to come up with an algorithm where high weight elements are chosen before, and then you go to like smaller and smaller weight elements. Big decision first principle, you want to say like that if your model permits, so for some uncertainty problems, you can follow this recipe where I first select the high weight elements, then lower weight, and then lower weight. Whereas for some models, this is not possible. So this is what we are kind of saying that, okay, if it is allowed, then you are able to save the extra log factor. If it is not allowed, you're going to lose this extra log factor. More precisely, like for these three problems. So the secretary problem, where elements come in this random order, as I was saying, like the right answer turns out to be a single log, and you don't have to pay this extra log. So it's not log square, it's a single log. Morally, we basically say like because elements come in a uniformly random order, you can come up with some kind of an algorithm which initially just focuses on high weight elements, then gradually it reduces its threshold to getting going. In the profit model, which is another model where elements come in some stochastic setting, but they come in an adversarial order. Here it turns out that the adversary can really force you by first presenting all the low weight elements, then gradually higher and higher. So it's like totally the opposite. And here your algorithm has to incur an extra log. Right answer turns out to be around log square. Similarly, for stochastic probing, again, the adversary can do better. Right answer is log square. And all of these bounds are tied up to polylog. This is the main message. Like, yeah, the next 3 slides, I'll maybe give like a high-level idea of how we go. Good. So the question is like, do I need the range of the values? Because I was assuming like on the first slide, all the weights are between 0 to 1. So this is usually without loss of generality. There's always like, because you have like either a distributional knowledge about these stochastic problems, or in random order problems, you can always like ignore the first half of the elements to get some estimate of the value. So like up to constant factors, you can always assume that the range is. Okay, good. So let me just give a high-level idea, like how we go about. So let's first recap how the unweighted algorithms work. So as I was telling, for each of these 3 problems, previously we knew a log-in guarantee, log-in approximation, comparative ratio kind of a guarantee. And how did these algorithms work? Like, so these are like works of for secretary and profit. This was known due to Aviad's work years ago, and for stochastic probing, this was shown in last year talks. Roughly, these algorithms work in the following sense. There's some kind of a greedy algorithm. So you basically want to select the next element if it is firstly feasible to take. Also, it should not hurt your value, somehow like hurt your value from other elements. Now, there's some kind of uncertainty. You don't know the exact values of these elements. So what you do is like either you kind of hallucinate a sample from the underlying distribution, or like, yeah, basically you take a sample from the underlying distribution and try to see how your greedy algorithm performs on this sample, and accordingly try to make a decision. That's the high-level overview. And so the algorithm is quite natural, and but it's not clear why the algorithm should work. Because you might be very much like overfitting to this underlying sample, the sample that you took. Initially, this sample is a very good surrogate for the distribution, but gradually it may not be. And so the main idea of these prior algorithms was somehow like to argue that no bad solution, like by bad I mean like let's say like a small cardinality solution, small size set will be selected. So the proof usually goes in 2 steps. Where first step is the difficult part, but basically that step ends up arguing that any particular bad solution, it's going to be rejected by your greedy algorithm, at least like with like exponentially small, large probability. Any particular bad solution, which is like a solution of small size, will be rejected with very high probability. And the next observation is the number of small sets is actually small. Because let's say you have n elements. If let's say all solutions are of size at most k, there will be like of size at most n choose k. Like n choose 1 plus n choose 2 up to like n choose k. If k is small, then there are not too many such solutions. So you can afford to take a union bound over all possible small sets. Basically, that's the high-level idea, that they basically argue that any particular bad solution is exponentially unlikely to be selected, and then you take a union bound over all possible bad solutions. By bad, I mean small set. Trying to extend this approach, this was all in the cardinality set, in the unweighted setting. But when we go to the weighted setting, the problem becomes like there are different scales. Let's say even if you have 2 weight buckets, there's a large weight bucket, which is, let's say, like square root and factor large values compared to the smaller weight bucket. But the number of small weight elements is much, much larger, because maybe both of these 2 buckets are contributing roughly the same amount of value to opt. Now, the problem becomes that the concentration inequalities will roughly, let's say, from the perspective of the high value elements, the expect concentration will be roughly like e to the minus the number of high level elements. But the number of algorithmic configurations is much, much larger. It will be like e to the number of low elements. So you can't take a union bound because there's a scale mismatch. Like concentration is happening at the level of number of highs, whereas the number of solutions is exponential in number of lows. So that's like roughly the setup. And so from this, like, okay, now this is where like the idea of this big decisions first, or like we're trying to make solution decisions for the high weight elements first will help. So for instance, in the secretary problem, like the random order setup, as we were saying, like we are able to get a single log guarantee for this weighted setting. The setup here is like one idea that we kind of exploit is your algorithm, let's say, goes in decreasing order of weights. Suppose it can somehow achieve that. Then the benefit is that, like, let's say I'm picking up first the high weight elements, then the concentration inequalities are still of the order of like e to the number of like negative number of high elements. But because my algorithm hasn't selected any lower weight element yet, the number of possible solutions is much smaller. It's only e to the high. It's exponential in number of high elements, not exponential in number of low weight elements. And that's why you can now afford to take union bounds. So basically, if you go in decreasing order, like basically in some sense, like if I'm looking at high weight elements, the number of high weight elements is smaller, and hence, and low weight elements are anyways like not interfering. That's why the union bounds can be made to work. So that's the high level intuition, like formally why this big decision principle, like kind of going in decreasing order of weights helps. The other thing is, of course, like in random order and so on, you cannot really just go in decreasing order of weights because, I mean, the elements are coming up mixed order. But what we are able to show is like somehow you don't have to really look at, like if I want to solve just the high weight problem, I don't have to look at all the elements. I can just look at the first 1 over log n fraction of the input, try to get some like a log n approximation for the high weight elements, then look at the next 1 over log n fraction of the input, try to get another log n approximation for the second class, third class, and so on. So, question, yeah.
So rather than like picking one scale,
Yeah, so we are gradually decreasing the scale. Like start with the largest scale, like scale 1, then half, then quarter, and so on. That's the high level idea. Of course, to make things work, like you need to be very careful. A lot, like a bunch of subtleties. On the hardness side, as I was saying, let's say like in the profit setting where elements come in a adversarial order, there we are showing there's a better hardness, like a log square n hardness. And morally, we want to say like somehow that whatever is the unweighted hardness, unweighted log n hardness, we want to somehow like make it worse by using weights, increase that log to log squared. So morally, we'll have some kind of a layered structure where the topmost layer kind of represents, where each layer kind of represents some hardness for the unweighted problem. You want to say like somehow the optimal solution will get some nice value from each of the layers, whereas the unweighted solution will be losing log factor in each of the layer. Moreover, it will only be getting value from only one of these layers. Naively, if you try to again implement such an idea, the problem is that the number of elements that your ground set will blow up. It will become like from n elements, it will become like exponential in n elements. So you'll not be able to get good guarantees. So the way we are able to make this argument formal is by somehow like having elements being repeated several times in this tree and combining it with some kind of an error correcting code. Like the error correcting code ensures that although these nodes are not, like these elements are not distinct, there are overlaps, but they don't hurt us too much. So we end up using 2 error correcting codes, like 1 per each layer and 1 per every root leaf. So to summarize, we studied these 3 problems, the secretary, profit, and the stochastic probing. For each of these problems, we've been able to resolve this log versus log squared n gap. And the interesting thing is like the underlying intuition is the same for each of them. You want to go in decreasing order of weights. For problems where you can design a good algorithm implementing this thing, you get a better guarantee. But if you cannot, then this intuition also helps you come up with a good hardness example. Some of the future things to work is like firstly, like poly-log-log factors are still quite open. Resolving them is interesting, like even like major, like even for special classes of downward closed set systems, such as matroids, the major open question matroid secretary, which is open for like 20 years, is getting a constant for matroids, where again the unweighted problem, trivial algorithms, greedy algorithm get you one approximation, but for the weighted guarantees, the best known are like log-log. So it's a major open question to get like how to reduce that log-log. And the other thing is like maybe this big decision principle could be useful for other problems. Thank you.
Any questions? So maybe that is
Is what?
so you can do that. Is there any that should be just
So actually, I think there should be a better algorithm. In particular, for the last year's Fox paper showed that for one of these unweighted problems, you can actually get a log over log log. So they actually shaved off the log on. So there are better algorithms to be potentially achieved. So
and so this allows something somewhere.
by log n squared, yeah, you potentially could get like log n squared divided by log log squared or something.